Welcome back for another lecture, this one on Earth's oceans. It's kind of a long one. We'll kind of zip through it a little bit, but it does cover quite a bit of content. So this is really kind of like your full-on crash course into oceanography. The other videos I posted, I introduced really the fundamentals of coastlines, some of the features, looking at the differences of waves and tides and currents. So this one's going to be a little more about how do we understand the oceans, how do we see the oceans, and what are the different attributes and levels. So let's just jump in. So the vast world ocean. So there's really just one ocean, right? So we're identified as the blue planet. About 71%, about 3/4 or so of our planet is covered by oceans, by one ocean. Or 4 ocean basins. Oceanography utilizes geology, chemistry, physics, biology, all of that to study the oceans. A lot of people take oceanography as a course and are like, well, what are we going to talk about all the dolphins and the whales? And it's like, that's more of a marine biology course. Oceanography is really about understanding the fish bowl and all of its contents and how it works and the chemical composition. So it's a little more complex than just the animals that get to play around in it. So we have 4 ocean basins. We've got the Pacific, the Atlantic, the Indian, and the Arctic. Beyond that, we do have other regions that we identify as seas and stuff like that, but these are the big 4. So the Pacific is the largest, has the greatest depth. It covers about 30% of our planet. The Atlantic is about half the size of that and only covers about 20%. The Indian Ocean is a largely southern hemisphere body and significantly smaller than the Atlantic. And then the Arctic is the smallest. It's only about 1.5 times the size of the United States. So it's actually the smallest ocean that we have. But again, we have these 4 ocean basins. So how do we map it? Well, we know way more about space than we do our oceans, which I think says a lot with just how we look at TV, right? There's so many different television shows that deal with space and the frontier, but we don't really have a lot of well, okay, we've got what's that, the one with the sharks and stuff, Sharknado, but those aren't real scientific videos and television shows. But looking at mapping the ocean floor, so we use bathymetry, which is a measurement of ocean depths and topography. We use sonar, satellites, submersibles. They allow us to study the ocean floor more efficiently. We really didn't know a lot about what was underneath the oceans until World War II, when we started using sonar and looking at the ocean floor. By looking at the ocean floor then, it allowed us to understand that we have divergent zones, that we've got these rifts, and that's when the whole the information that was needed to prove the theory of plate tectonics was then developed, because then we had that last nail in the coffin. We can now prove beyond a reasonable doubt this is how the bigger picture works. So we look at all these different things. So what I did is I just chose a photo of a map itself of the world and showing all the different continents and then the ocean floor. So let's talk about some of the ways that we map it and produce this bathymetry, which is these beautiful maps that show what the ocean floor looks like. And a great example of this would be looking at Google Earth and flying over the oceans and seeing all the depth, looking at the volcanic arcs and looking at all the different attributes. So the first one is we'll look at a sonar, which I don't know if I didn't know that the sonar is an acronym for sound, navigation, and ranging. So it's a transmission of sound waves towards the ocean floor. So the way that it's essentially done is they send down a sound, and then the sound bounces off the floor and comes back up like an echo, right? But based on how long it takes that echo to come back, gives us a calculation of the depth of the ocean floor. So then we're able to then, read that. So this is the way it was done. We still do this a little bit. Now we do a lot more of the digital scanning that's able to get us down there. Looking at satellite imagery, so it measures small differences using microwaves. So this provided that not all ocean floors are flat themselves. So looking at satellite imagery, not just photography, but looking at, again, the different waves that are sent back and forth, looking at color imagery and looking at depths that way. So there's lots of different attributes that we can look at, but these are all different ways that we can visualize the ocean floor. So here we have a satellite in orbit, outgoing radar pulses, and then they bounce back. Here we have the elevation of the sea, the surface height, ocean floor, and we return the pulses from the sea surface. So I think it's this kind of, you've probably seen this before at some point. But let's talk about the margins. This is really important for us because we are surrounded by margins around our continents. So the continental margin is a zone between the continents and the ocean basin, being really looking at the continental crust moving into the oceanic crust. And the margin itself is that transition zone. If you notice on top of this, we have a shelf. This shelf is material that's been deposited out into that transition zone. So in the Atlantic, thick layers of sediment cover continental margins, low volcanics, and limited earthquake activity. So we have all of this going on in the Atlantic. The Pacific, we have a very short continental shelf because we have a margin. Looking more at the Atlantic, they have a much longer shelf. What's interesting also about the margin itself, looking at places such as Florida, we can see that this is where, because it's very shallow, where a lot of their coral reefs were developed, because coral develops well in shallow, warm water. So it usually develops here on a margin itself, on the shelf. Looking here at this deep sea fan, that's interesting. This is really essentially you have a submarine canyon. All that material, the submarine canyon is where all of the sand that's along the beach line will drain out into, and then create this fan shape down here into the rise, and then the abyssal plain. The abyss is out in the middle of nowhere. It's super, super, super far out there. So anyway, we have these margins. If you remember from one of our activities, we cut out the different continents, and we took them as they look today, including the shelf, and then we had to merge them back together to replicate Gondwana. Looking at one of our tectonic spooning events. And in doing that, you had to use the shelf as part of that seam to put these back together. So maybe that brings back some memories. So some of the ocean floor features, we've got then the continental shelf, submarine canyons, and then turbidity currents. So I'll take a moment to introduce each one of those. So again, the continental shelf is a gently sloped submerged surface that extends from the shoreline outward into the ocean. It can contain important mineral deposits, oil, natural gas, and gravel. That being said, within the continental shelf, that's where they do a lot of offshore drilling. In Florida in particular, that's where they get a lot of their natural gas reserves. For us on the Pacific, in California, that's where we get a lot of our oil reserves. These submarine canyons are seaward extensions of a canyon that's been carved into the outer continental shelf, in which the longshore current brings material along the beach, hits a submarine canyon, and takes that material out into the ocean and beyond. And then a turbidity current is a downslope movement of sediment laden water, so it means it's like mud, and that's caused when the sand and mud of the continental shelf are dislodged and become suspended. So imagine really a turbidity current is like a landslide of material that then breaks off of the shelf, goes out into beyond into the abyss, but all of that turbidity just means that it's muddy and murky because all that material has been resuspended and will then have to be laid out and deposited. So looking at some of these things, I found this diagram, I thought it was quite helpful. So here we have our submarine canyons, here we have this material that builds up, and here they give an example of a turbidity current. What's interesting about these, they can also be graded bedding. So looking at what we consider Sedimentology, which is in the geology family, is that then they would look at these different layers and see that these are different events. We find that generally the coarser grain material will deposit first because it's the heaviest, and then you kind of work through your different layers of grain size. So you need a lot of energy, a lot of material to move bigger grain stuff. Then you have, medium, very, then maybe very fine, coarse, medium, fine, coarse, medium, fine. So in this particular image that they're giving us, we have 4 visual turbidity currents that have deposited on these fans. This also can give us some information about some of the local geology, looking at the different material that had been deposited within the shelf over time. So again, this doesn't have to just be sand. It can, maybe there's been volcanic events, on the land or maybe nearby that have put in ash, maybe looking at different broken bits of coral reef. So it's different ways that we can look at the localized geology. So here's 3 more. We have continental rise, the abyssal plains, and seamounts. The continental rise is a gently sloping surface at the base of the slope because it's rising up. The abyssal plains is a very large area of deep ocean floor. That's why I keep referencing it's the abyss. It's way out there, and it's just very, very vast. And then seamounts. They're isolated volcanic peaks that rise at least 1,000 meters above the ocean floor. So meaning that these seamounts are essentially volcanic mountains, that these volcanic mountain ranges that exist very, very deep beneath the ocean. So like we like to think in California, that we have Mount Whitney, which is like our Everest at over 14,508 feet from zero upward. But if we were to then look at the landscape and remove all the ocean water and look at some of the mountain ranges that exist on the oceanic crust and their height, that's actually some of the tallest mountains, and some of the deepest holes in the world are found out in the oceans, because you have to take from their surface to their peak, which is pretty impressive. So here's a diagram. So this is really neat. This is using a scan. So what they've been able to do here is we can see down below, this is your oceanic crust, this is your volcanic peak. These are all different deposits. This is sedimentary geology right here at its best. Different layers of material. So what this scan was able to do, was able to then obtain and read this harder igneous rock, and then and be able to distinguish the densities and thicknesses of all these other sedimentary layers that lie on top. This is important because it gives us a better image to understand what's underneath. Because if you were just scanning the top, you'd see this one volcanic peak and not understand that there's so much more oceanic crust that's not been observed because it's been covered by all of this material. So what about some of those sediments? So here we mentioned there's different sediments here, but what are those? Well, here's some different types of sediments. You have biogenous sediments, which consist of skeletal remains of marine animals and algae. You have calcareous ooze, which is like a thick ooze from the dissolving calcium of carbonate shells. You have siliceous ooze, which is silica-based. It's an ooze composed of silica-based single-celled organisms and algae. And then you have a hydrogenous sediment, which is the mineral crystallization from the ocean waters through chemical reactions. So these are four very common sediments that we observe on oceanic floors: biogenous, calcareous, siliceous, and then hydrogenous. The one that I think is the most interesting is the calcareous ooze, just because it's kind of fun to say. But even looking at the biogenous sediments, they consist of skeletal moraines of marine animals and algae. Perhaps you've seen chalk, like on a chalkboard. That's usually biogenous sediments, looking at chalk, because that's broken up skeletal moraines in oceans. So looking at the White Cliffs of Dover is part of that material. Break time. Okay, just a couple more slides. So that was really crash course in understanding the Earth's oceans, how we very quickly look at it. Again, this is to complement a lot of the material that you have in the course. So let's look more at the seawater. So we've now very briefly looked at what we see on the ocean floor, but what about the oceanic water? Well, let's first speak about salinity, or salt. So we know that salt exists on our planet. It's a natural mineral. It comes from rock. We know that if you've ever boiled water and you forgot about it and you come back and there's just white powder in the bottom of the pan, that is because the water can evaporate and it can go away. But it cannot take the minerals behind. And those minerals that are left behind are called evaporates, right? Because you've evaporated all the water, leaving those minerals behind. So what can change salinity in the ocean? So if you want to decrease the salt in the water, in the ocean, you either have advanced or progressed precipitation, you have sea ice and icebergs melt, or you have more runoff. So essentially, to decrease the salinity of the ocean, what do you need to do? You need to add water to the ocean. There was a saying a long time ago, it's not true, but it was the solution to pollution is dilution, right? That's not true, but they used to think that, because if you if you continue to dilute that, it'll become so small that you'd hardly even notice that it's there, but it never really goes away. So it'd be kind of like getting, I don't know, like a glass of water and putting a little bit of salt in it, and then trying to add more and more water to it to try to flush out the salt. But you can never really get rid of the salt. You add more water to it, which makes it a lot weaker. Well, how do you increase salinity? Well, by advanced evaporation or by glaciations. So by maybe the ocean waters getting a lot warmer, by more radiation being absorbed by the oceans and planet, creating warmer air, can increase evaporation rates, so taking water out, leaving the salt behind, it becomes saltier. Uh, Glaciation, so again, water is being pulled out of the oceans and being stored in the landscape, leaving more salt behind, right? So imagine maybe you are making a top ramen, with the square and the salt powder, and you put it on there, but you forget about it. You boil it after you've added the salt, and most of the water has gone away. You'll notice that it's almost like a syrup. It's so thick, right, because of that salt. So you have to add more water to it. Well, that's what happens here. By evaporating that excess water, it becomes a lot more intense. Looking at salinity, so there are measurable proportions of dissolved material in water that can be expressed as parts per thousands. So what we can do is we look at water and try to see what's in it. So obviously within the ocean we have water and salt. Are there other things? Yes. There's lots of other things. There's nitrogen and carbon and all kinds of other elements that have been absorbed within it. But think about just like your drinking water, right? In your bottled water that you buy at the store, think of all the things that have been added to it. You can't see it, but it's there. And you know it's there because if you're like me, you know that there's a definite difference in taste between Dasani and Aquafina. I can't stand either of those, but if I had to drink one, I'd drink Aquafina. I don't know why I think Dasani is terrible. But there are then measurable proportions of dissolved material in that water that gives it the flavor that you want, right? Think about it. It's like the difference between Coke and Pepsi. Some people like Coke, some people like Pepsi, and there's people who do not like Coke and do not like Pepsi. And it's because there's something in that solution that either you like or you dislike, but you can't see it. You just can't like pick it out of there, right? Most of it's sodium chloride, which is table salt. Sources include rocks and chemical weathering of the rocks and minerals. That's where it comes from. There used to be the saying that when you're out, if you're ever stuck in the desert and you're dehydrated, to just grab some rocks and stuck on a rock, because there's usually salt on the rocks themselves that will help you help make your mouth water so you can try to retain some of that moisture. I'm not saying you should go suck rocks. I'm just saying that was a thing. Well, because of this composition of seawater, this kind of reflects on an earlier presentation, we can create density. So changes based of salinity and temperature can create density. So saltier and colder water have a greater density and are able to sink. So this is really looking at these current systems. So we have deep current, cold, salty water that can mix with shallow, warm water. And so we have this cycle in which water can then travel. This is really important for really the whole biosystem, ecosystem, and our landscape, right? Because by having this constantly moving water, you're moving temperature around. So you're taking warm water, mixing with cold water, and making cool water. You're also taking all of the material, so usually plankton, phytoplankton, stuff like that, that able to be able to mix some of that around. But then you're also allowing corridors for animals and other things to kind of like a freeway system that they can jump into to migrate. So looking into that, this is a little diagram showing then looking at temperature. So ocean surface temperature varies because of solar radiation. So this thermocline is oceanic water between 300 meters and 1,000 meters in depth, where the dramatic temperature changes with depth. So it creates a barrier, essentially, in marine life. So what I have, I tilted this diagram on its side. So we can look at then, these are latitudes going across. And then we can see temperature and salinity. So temperature is observed in the red, salt is observed in the blue line. So we can see at the equator, which is where it's usually the warmest and most consistent, the water is much warmer, right? But because it's warmer, we also find that it's less dense. Well, that's weird. Why would you think that? I'll give you a minute. Well, what happens in these areas? It rains a lot, right? So then you're going to find that there's a flux in that amount of precipitation, changing the salinity. Look at places where it doesn't rain as much. We can look at areas like this, 40 north, 40 south. We can see that the water is starting to cool down. We have this another barrier that builds in here. See these barriers that exist. So anyway, just another diagram to kind of put it in perspective. So let's talk about the diversity of life. this is as far as we're going to go into life. Again, marine biology is a course that you would take to learn about it, but we like, as oceanographers, to look at the diversity. So marine organisms are classified really by their location and their motion. We find that it's very easy to classify things like that. Another thing that we classify very similar would be clouds. We're looking at atmosphere. We classify clouds based on their altitude and the way that they look, their shape. So we can really do a lot with those two elements. So we have the plankton, necton, and benthos. So plankton are all organisms, animals and bacteria. They just drift. They have no control over where they're going. They're just floating around. They don't have the ability to really be able to control their location, right? Necton are all animals capable of moving independently. So they have fins. They can control exactly where they're going to go. And then benthos are the ones that live on the floor. So these are like your crabs, your sponges, stuff like that that live on the bottom. So, I don't know how, if it may help, but looking at plankton, necton, and benthos, there's often a comparison with SpongeBob SquarePants. Who would be what, right? Who would be, plankton, who would be considered a necton versus who would be a benthos. So looking also with diversity of life, we have these zones. We have the pelagic zone, the benthic, and the abyssal zone. So the pelagic zone is of any depth where animals are able to move freely and swim around. The benthic are sea bottom surfaces regardless of distance to shore. And then the abyssal zone is a subdivision of the benthic, it's extremely high pressure, very low temperatures, low oxygen, and very limited to no sunlight. There's too many commas there. I'll fix that. So think about with in the news all the time. I don't know why it always happens to be somewhere near Russia, but it always seems to be in Russia where they come up and say, look, we found these fish or this marine life that we've never ever seen before, and it's usually observed and picked up out of a place out of the abyssal range because it's really, really high pressure, very, very dark, very, very, very cold. So it requires a lot of work, usually it's very rare that you'd send a person down to this type of zone because it's just not safe because they could get the bends on the way up, and also because it's very hard to control all that pressure and it's very expensive. But they usually send some form of robotic down there to capture these things. So the pelagic, the benthic, and the abyssal zone. Which brings us to this diagram. This is that classic, what I like, putting it together. So how can we see everything together? Again, so we can see all these different zones. Here's the benthic, the abyssal. Then you can also see the pelagic zone. Are there other things on here? Absolutely. I wasn't going to try to Photoshop everything out of here, but I think that this really helps put things together. Here we have our continental shelf. Here you have your high tide mark, low tide mark, your beach, your coastline. So you can start seeing how all of this somewhat merges together with the previous presentation that I've posted. So diversity of life. What's interesting here, sunlight. The sunlight is, backtracking a little bit. The sun gives off visible light. The visible light itself is not hot. It's very, it's a shortwave radiation of visible light. What ends up happening is that surfaces are able to absorb that light and then transform that energy into long wave radiation, which is identified as sensible heat, which means you can touch it. So as you can see, it's a very small area of the ocean on the top that's able to absorb that sunlight, right? The ocean reflects a lot of it, but it's able to absorb a little bit. And in doing so, what they're calling the photic zone, that's going to be your warmer waters. That's going to be the areas, especially over here, where you're going to be able to develop coral reefs. What's interesting about this is that maybe you've experienced this very bad example, but like in a pool, like someone's big backyard pool, where the water is really warm right here in the shallow end, and all of a sudden you go to the deep end and it's freezing. Well, that's essentially the same idea, is that the sun is only able to reach and go through a certain depth of that pool, and then everything else below, it just gets really, really cold because it's cold, dense water, right? Brings us all back to that. All right, well, I know that was a lot of information, and I know I speak fast, but I just wanted to kind of jump through this to give you an idea of what really Earth's oceans are about, how we look at it, the words that we use, the different types that we do, looking at the different diversity of life, looking at those three families, try to break things up into categories such as that. I hope you enjoyed, and we'll talk soon.